All right, class, we're going to do part 2 of our Chapter 5 outline and continue with the normal model. So there's no universal standard for z-scores, but there's a model that shows up over and over in statistics, and the model is called the normal model. You may have heard of this as a bell-shaped curve. It's going to show up in all the statistics, and the thing is, if you have enough data, and you take enough samples of data, eventually the average will become a normal model. So this is just a key thing in statistics to know, and it's going to show up a lot. So normal models are appropriate for distributions whose shapes are unimodal and roughly symmetrical, and the model is written as in parentheses mu comma sigma. That's a sigma sign, and it's for standard deviation. So that's mean and standard deviation. And what we're going to learn is if we have enough data and we have enough samples, virtually every distribution, the mean of it becomes unimodal and symmetrical. So these distributions provide a measure of how extreme a z-score is. There's a normal model for every possible combination of mean and standard deviation. So we write n mu sigma to represent a normal model with a mean of mu and a standard deviation of sigma. We use the Greek letters because this mean and standard deviation are not numerical summaries of the data. They are part of the model. They don't come from the data or the samples. These are the true values that represent the full population. So these are measurements of mean and standard deviation of a full population that you have taken and found the statistics on. Such numbers are called parameters of the model. So it's a parameter if it's over the entire population. Summaries of data, like a sample mean and a sample standard deviation, are written in Latin letters. Such summaries are called statistics. These are called statistics if you're just looking at a sample of data and not all of the data. These are calculated values that represent a sample. When we standardize normal data, we will still use the standardized value, a z-score, but we write it as z equals y minus mu over sigma. So we're going to have that same z-score except with a mu and a sigma on it because we're using the entire population, right? Once we have standardized, we only need one model. And it's the normal model N01, which is the standard normal model when we put things in terms of z-score. Because with a z-score, remember, the average is 0, because right in the middle, z-score is 0 at 50%. And the standard deviation would be 1 because you divided by the standard deviation and turned it into 1. So you got to be careful. Don't use the normal model for just any data set, since standardizing does not change the shape of the distribution. When we use the normal model, we're assuming that the distribution is normal. We cannot check this assumption in practice, so we check the following condition. A nearly normal condition that the shape of the data, the distribution of the data, is unimodal and symmetric. Looks like a bell curve, like a bell shape. So we want our data to kind of look like, let me pull up the pen real quick, unimodal and symmetric, kind of like this. And there would be the mean right there. This condition be checked with a histogram or a normal probability plot. So we'll explain a little bit of that later. You can look at a graph and kind of tell if it looks normal or not. The next thing we're going to talk about is the 68, 95, 99.7 rule. Normal models give us an idea of how extreme a value is by telling us how likely it is to find one that far from the mean. Because the further you get from the mean, the more extreme that value is, right? Like if the average score on a test was 50, somebody that scored 100 scored an extremely high score. Like, well, that should be very rare, right? The same way if the average is 50 and you score a 0, that's extremely low and extremely rare. We can find these numbers precisely, but it's useful to begin with a simple rule that tells us a lot about the normal model. If data follows a normal model, this is called the 68, 95, 99.7 rule. About 68% of the values fall within one standard deviation of the mean. So, if your mean was 100, and your standard deviation was 15, 68% of your values would be between 85 and 115, right? Because you go one standard deviation in both directions. About 95% of the data would fall between two standard deviations of the mean. So that would be between 70 and 130 if you had a standard deviation of 15. And about 99.7, nearly all values fall within 3 standard deviations. So numbers outside of this are crazy unlikely. Very unlikely. And that would be between 55 and 145. So if you got data that was like 160, that would be extremely unlikely. It's possible, but it's extremely unlikely. And you absolutely want to draw this right here, the model of the 68, 95, 99.7 rule. Say you had the middle right here, and the mean was 100, and the standard deviation was 15, like on that previous one. This mean right here would be 100, right in the middle. And 100, one standard deviation above would be 115. 2 standard deviations above would be 130. And 3 standard deviations above would be 145. A standard deviation below would be 85. And then 2 standard deviations below would be 70, this right here. And 3 standard deviations below would be 55. And what this tells us is 68% of the data is between 85 and 115. 95% of the data between 70 and 130. And 99.7, nearly all of it between 55 and 145. And as long as your data follows a normal distribution, this will always be true. It will follow this rule. So this is very useful for normal distributions. And what you're going to learn later, in the later chapters and later in this class, is if we have enough samples and we have enough data, we're going to be able to turn nearly everything into a normal distribution when we're looking at the means, the averages of certain data. As long as you have enough data, it all starts to become normal distribution. And so that's why this is such a vital thing to learn in statistics. It can be used in all sorts of studies and research and, scientific, collecting samples, trying to prove something. If we're going to prove a hypothesis, we're going to use this a lot. So that is the end of this chapter. And next I'll be doing some of the examples, and we'll do that on the next video.